We propose a new method for single monocular image depth estimation. It is a challenging problem due to its ill-posedness nature and has found wide application in industry. Previous efforts belong roughly to two families: learning-based method and interactive method. Learning-based method, in which deep convolutional neural network is widely used, can achieve good results, but they suffer low generalization ability and typically performs poorly for unfamiliar scenes. Besides, data-hungry nature for such method makes data acquisition expensive and time-consuming. Interactive method requires human annotation of depth, which however is erroneous and of large variance. To overcome these problems, we propose a new perspective for a single monocular image depth estimation problem: size-to-depth. The main challenge for this problem is the inherent ambiguity of single monocular image. As is in the picture, the object on near plane and far plane produces identical image on the camera, while their depth vary over a wide range. Such phenomena accounts for the strong ill-posedness of depth estimation on single image. For images of real scene, object prior is a clue to resolve the ambiguity of depth. While the object plane has infinite possible position, many of them correspond to impractical real-world size of object. By introducing prior of object size, which rules out less possible cases, we will achieve much better approximation of depth value. Following basic geometric relation, for fixed focal length and object size in photo, depth of object is proportional to its real-world size. Thus, size is equivalent to relative depth, and we can calculate absolute depth given the camera parameters. This is the basic philosophy we follow in this work. Our method requires sparse label for real-world size of object rather than raw depth, which is a faster and more efficient labeling technique. We divide input image into small patches and label size of dominant component of each patch. A coarse depth map is then obtained, following geometric relationships according to size labels. Then we refine the depth map by doing energy function optimization on conditional random field. Energy function for CRF consists of unary and binary terms. Unary term require the refined depth to match with coarse depth of its belonging patch. It will constrain the global layout of depth map to be relatively reasonable. Binary term penalizes depth gap between neighboring pixels, which encourages local continuity of the depth field. Similarity function is defined to be image gradient between pixels. And finally, maximum a posteriori on CRF gives the normalized depth prediction. Here is some of our results. In conclusion, we propose a new perspective for single image depth estimation. Our method produces satisfactory depth map. Compared to traditional interactive method, our method is faster and more accurate. And compared to learning-based method, our method has better generalization ability.